Feedback systems are usually designed with the familiar single-loop block diagram in mind. That is, the major loop feedback path is designed to have a transmission function such that the specified gain is achieved in the presence of non-infinite major loop gain. Various non-idealities, such as unavoidable minor loops and direct forward transmission, make the single-loop block diagram progressively less useful, especially at higher frequencies. In conventional analysis, attention is usually focused on the loop gain T, which is calculated by injection of a test signal into the forward path. There are two deficiencies in the conventional approach. One, the right answer for T is obtained only if the test signal is injected at an ideal point, such as at an ideal dependent generator. 2. Non-idealities are ignored, as is tacitly conceded in representation of the forward and feedback signal paths by arrows to exclude reverse transmission. The General Feedback Theorem overcomes both deficiencies and provides additional benefits. 1. The loop gain T is calculated by injection of both voltage and current test signals at a non-ideal injection point. 2. Calculations are performed on the complete circuit model without the constraint of unidirectional paths. 3. No assumptions or approximations are made, so the non-idealities are included. If the voltage and current test signal injections are made at the error signal summing point, effects of the non-idealities can be evaluated separately. 4. The GFT dissects the closed-loop gain into 3 of 4 constituent transfer functions, each of which is obtained directly in terms of the circuit elements, which makes it possible for the results to be used backwards for design. This is the principal objective of design-oriented analysis, the only kind of analysis worth doing. The GFT defines a natural block diagram model that is identical in format to the single-loop model that is conventionally assumed, thus providing a link between general feedback theory and a detailed circuit diagram analyzed in terms of factored pole zero transfer functions. The natural block diagram emerges as a result of the analysis, not as an initial assumption. Although the GFT can be employed in symbolic analysis, it is also computer-friendly. Intersoft's ICAP4 design simulator product line includes GFT templates and also a user's manual. The GFT template quickly makes available Bode plots of all the simulated and post-processed transfer functions. A reduced template produces the loop gain only and reads out the phase and gain margins. In the CD, the GFT is illustrated on a two-stage feedback amplifier having various non-idealities, including loading interactions at all points, direct forward transmission, and 2 minor loops. Another illustration investigates the potential instability of a Darlington emitter source follower. The GFT applies to any transfer function, including not only voltage and current gains, but also transfer gains and input and output impedances. It can also represent the extra element theorem to spotlight exactly how one or two selected elements affect the system performance. The GFT can be applied to any system representable by a linear model, such as switching power converters, servo systems, and is especially useful in analog high-frequency ICs where the non-idealities eventually control the performance. Well, it's a pleasure to be back at APEC after an absence of several years. I've given 5 APEC seminars previously. This is sort of a structural view what happened. The design-oriented analysis, shortened to DOA, don't forget the hyphen. This has been my main topic for a long time now. And what I usually start out talking about, as I did in that seminar back then, was the premise for talking about a lot of basic techniques which I've found to be very useful, and I hope some of you have also. And the starting point for that was a recognition quite some time ago that most of us come out of college all ready to go and be design engineers, and we fall off a cliff. This is the very first one I showed, where I established the premise for all of this stuff. You get force-fed as a student, and you go out into the real world and you fall off the cliff because the first time you try to apply all that good stuff, you get stuck. So you abandon it and you restart, and you begin the much longer process of learning by experience and all the other empirical methods. Well, I finally decided to pretty up this picture a little bit. So it might make it slightly more memorable, but if not, then we haven't lost anything. What is design-oriented analysis about? The main thing is you have to get the analysis result in what I like to call a low entropy form, so that it can be worked backwards. Well, what does working it backwards mean? The low entropy expression is one in which terms are grouped and ordered so that you get additional insight into the relative importance of the various contributions to the result. Why do you need to do that? Because only a result that can be worked backwards is of any value in doing design, because design is the reverse of analysis. In design, you start with the answer. The answer is the specification of the part that you have to build. So the answer to the analysis is what the system has to do, and your job as a designer is to work backwards as to what stages to put together, what components, what values to choose. So any analysis that you do that ends up with a huge expression saying gain equals, and on the right-hand side of the equals is a ratio of sums of products of all the elements in the system, that is absolutely useless for working backwards. All you can do with that is put in a given set of numbers, which you guessed at or borrowed from some previous project in the past, and you plug those numbers in and you get an answer for the gain, and it doesn't meet your specification. And so the next question is, what are you going to do with all of that? And the answer is nothing, because you can do an eyeball kind of analysis to try to work back to see where those components came from in the circuit, but that's a losing game in anything that's at all complicated. So that's the main point about design-oriented analysis. You have to keep control over the algebra and get a result that you can use backwards. Going back to the structure now, the extra element theorem I actually talked about twice. And the extra element theorem has two useful applications. There's a simple form of the theorem, and what it means is that if you've already calculated the gain, say, of some circuit, call that A sub infinity, and you decide after you've done that you need to add another element into the model, some stray capacitance perhaps, to see what effect it has, the conventional approach is to do the analysis all over again from square one, which is of course more complicated than it was the first time you did it, because there's one more element in it now. And you've probably done that a lot of times. And if so, you probably noticed also that great chunks of the algebra that you do resembles very closely to what you did the first time through. And you get the idea pretty soon that ought to be a better way of doing it. And that's exactly what the theorem does for you. Because instead of going back to square one and starting over, you start with the answer that you already had, which is the A infinity, so you know that. And all you have to do is to find those two parameters, ZD and Zn, which are the driving point impedances seen at the port where you are going to add the extra element. And ZD and Zn are properties of the original circuit. And they're pretty easy to calculate, usually. And then all you have to do to find the effect on the result when you've added the extra element is to plug into this formula. That's all you have to do, and you get the new answer in terms of the old answer multiplied by a correction factor that involves the element that you're adding. So the only work you're doing is finding those two driving point impedances, and that's done on the original circuit, and you never do any calculation at all on the new circuit in the presence of the extra element. Now, the other useful application for the extra element is if that's a benefit, the method I just described, then why not use that in the first place when you do the analysis for the first time? Leave out one of the elements, solve the simpler circuit, and then restore that same element by using this theorem. Again, the benefit is you never do a calculation on the whole circuit. Obviously, you can cascade that process, and you can simplify the circuit considerably before you start, and then add the extra elements one by one. And that's particularly useful if you designate a capacitance as an extra element. Because if the rest of the circuit is all resistive, then those two driving point impedances are also driving point resistances, and the Z is an S term, a reactance, and so the formula gives you the pole and the zero caused by that capacitor right off. In other words, the formula itself is a low entropy expression. You can see where the terms come from. You know what you have to change if you don't like the answer. Feedback theorem was one of the other seminars I've done a couple of times at APEC. I'm going to give a little longer summary of that because this is a lead into what we're going to talk about the rest of the time. This is the famous single loop model that everyone has in mind from the start. It's amazing how tenacious we are about hanging on to that model, even though it has a number of deficiencies. The conventional approach is you say the closed loop gain G is equal to the open loop gain A divided by 1 plus AK. And AK is the loop gain. And when I talk about this, I say pretty early on that I don't really like that formula. This familiar form really isn't the most useful form, especially with regard to electronic circuits, because the usual approach to analyzing the feedback system is to calculate A and K separately and put them into this equation and find the G. And that's not easy to do because in order to find A and K separately, you break the loop. And the problem with doing that is that when you break the loop, you actually change the values of A and K, because in most practical electronic circuits, there is an interaction between the two. In other words, this nice, simple block diagram is an oversimplification, because the two boxes are really not separable like that. So that's a basic problem with the conventional approach. And so I'm suggesting an alternative approach, which is potentially beneficial because not only is the A, for example, difficult to calculate directly itself by breaking the loop, but it isn't part of the answer that you're interested in anyway. The G is the thing that has to meet the specifications. That's what the ultimate outcome has to be, is the G. You as a designer are concerned about how you're going to get it, but someone else as a customer couldn't care less how you get it. He's going to buy the result, not the method. So if it's not only difficult to calculate A, and also you don't really care what it is in the end anyway, wouldn't it be better to have a formulation of the system basic equation which avoids specifying what A is? So it takes a very simple step to do that. All you do is take the original expression and you multiply top and bottom by k. So now you have ak over 1 plus ak, and ak is t. So the a has disappeared. I shouldn't really say it's disappeared, but it's become hidden. It's only inside the t. But it means we don't need to know what A is by itself. T is the quantity we need to know, because that's what the answer is expressed in terms of. And this is a much more useful version of the result anyway, because we can identify these two separate factors which have direct physical interpretation. In particular, the 1 over k in front is the limiting value that the closed loop gain is going to reach if the loop gain approached infinity. So it's a reasonable expectation that if feedback is going to be any use at all, the more you have of it, the better. Which means infinite t is the ideal limit. And so if you could make an amplifier with infinite t, its closed loop gain would approach 1 over k. So why don't we change the symbol? Because if G is going to approach this value, why don't we give it a symbol related to gain? So we'll call it a G, and we'll put a subscript on it as a reminder that this is a limit achieved if the t goes to infinity. Another useful thing about that quantity is that it's the only thing that we know when we start the design, because it's the specification. So here's that final result. And I rewrote it again in a slightly different form there to point out that the format is remarkably similar to the extra element theorem that we just had a few moments ago. The G infinity in front is like the A infinity. That's the gain before we added the extra element. The denominator is 1 plus 1 over t, where it was 1 plus zd over z, and the numerator doesn't have that extra term yet, but it should do. And that's one of the things we're going to talk about from now on, because that term is what needs to be added in order to account for a whole lot of non-idealities that are always present in any practical, realistic circuit. But the conventional model leaves it out. That gives you a kind of idea where we're going with that. So back to this list again. And this is now seminar number 6 after a considerable gap. And the background of this is that I've been struggling with this problem of how to analyze a feedback system without making assumptions and approximations in the first place. I've been doing that for a long time now. In fact, the first paper I wrote on it was 1964, 40 years ago. And the next one, and in that paper, I was talking about that missing term, although the notation was somewhat different then. Next paper I wrote was 1975, where I talked about how to measure the loop gain if you couldn't find an ideal injection point for the test signal. And there was a modification of that at the time as well. Well, 1975 is a long time ago, and I've thought about this problem on and off, mostly off, of course, ever since then. And on July 31st, 2001, at 4 o'clock in the morning, I had one of those little flashes of insight that I like to call a eureka moment. I suddenly saw how all this fits together. And I've been working on that pretty solidly ever since then, and this is the culmination of that. And as I was finishing up this kind of work and writing a paper about it, I mentioned to a few people, experts in the field. I was pretty pleased with myself for having come up with what I thought was this final solution. And they listened and looked a little mystified and said, "What problem? Hasn't the feedback analysis approach been settled for a very long time? What's the problem that needs to be fixed?" And so, in case you have some of that same idea, I'm going to go right now into what I think is a fairly convincing reason that there is something that needs to be fixed. Look at this rather simple two-stage feedback amplifier. Output voltage is fed back in series with the input. It's a series shunt configuration. The conventional approach to analysis for the loop gain of that circuit is to inject a test current at the output of the first generator. And what do you expect the shape of the loop gain to be? Well, there's only one capacitor in the circuit at the moment. So any signal entering the second stage device is going to look into a common emitter or a common source amplifier stage with a capacitor C2, which is in the Miller feedback position. So you'll get a large inverting gain at low frequencies from the second stage, and there will be a fairly low frequency pole caused by the C2. But as frequency approaches infinity, the C2 is going to look like a short. And so the gain is going to flatten out at a much lower value than it was at low frequencies, but it's going to be a non-inverting low value of gain towards infinite frequency. So you end up with a flat gain at low frequency and another flat gain at high frequency with a full phase inversion in between. So you get a pole from the capacitor at low frequencies, and the zero that you get at high frequencies is a right half plane zero, an RHP zero. So the asymptotic phase angle is 180 degrees from what it was at low frequency. So if you check that out by injecting a test signal and see what the answer is that you get, here's the method for doing it. Inject a test current IZ, it splits, IX goes forward, drives the second stage, comes back around to the first stage again, and when you do the analysis and plot the results, you get exactly what you expect. The gain is flat at low frequencies with a pole, flattens out again at high frequencies, and the phase goes to minus 180 and does not come back to zero, so it is a right half plane zero. So well and good. Nothing wrong with that. That's what you expect. There's the same circuit again, except it's got a C1 capacitor now, also in the Miller position with respect to the first stage. So qualitatively, what do you expect the loop gain to be now? In addition to the pole and right half plane zero from the second stage, you're going to get a pole from the first stage because you've got two reactances now. And you're also going to get a high frequency zero, but it's going to be a left half plane zero this time, because as far as the loop transmission is concerned, the first stage is acting in common base or common gate. So there's no phase inversion going from low to high frequencies. So the overall result that you would expect for the loop gain is two poles and a right half plane zero and a left half plane zero. So the asymptotic phase should be that of the two poles alone, which would be minus 180 degrees. So if you do the injection, this is what you get for the magnitude and phase. and is hopelessly wrong. The phase ends up at 0 instead of minus 180. Big difference. Now, why is this the case? Going back to the previous picture. Something's wrong with the place where we're doing the injection, or it's not, at least it's not giving the answer that we expected. And the reason for that is it's not an ideal injection point, because we've known for a long time that an ideal injection point is where you inject a shunt current at the output of a dependent current generator. And you can inject a series voltage at the output of an ideal dependent voltage generator. And there was only one of those two extremes available. But in the 1975 paper that I mentioned, I showed how to overcome that by doing a successive injection of a current and a voltage. Well, I didn't do that here, but this is a non-ideal injection point because looking back from the IY, it's not coming from an ideal current generator anymore because of the C1 capacitor. And that's why you don't get the answer that you expect from the loop gain. It's not that the calculation was wrong or incorrect, of course. It's that it's not giving you the answer that you wanted to get. So that's a sort of glaring example of what needs fixing. And even though this injection technique has become pretty widely known now, and it can be done in practice in the hardware as well, there's a caveat on whether or not you should believe the result. And the caveat is, what is the ratio of the impedances seen looking forward and looking backwards from the injection point where you're putting in the test signal? And that impedance ratio has to be infinite to do one kind of injection. It has to be 0 to do the other kind of injection, current versus voltage. That's why you get the wrong answer. This is not an ideal injection point. Now, how do we get to that situation? There's what the right answer should be for this same problem with both capacitors present. And you see, indeed, you have two poles in the magnitude, and then you have two zeros fairly close together above that, causing the gain to flatten out again, and the phase goes to minus 90 for the first pole and is heading towards minus 180 from the second pole, but then the zeros start to come in and you end up at minus 180 the way you should be. So the question before us now is, how do we get that answer? So I back up again now. This is the outline of what I want to talk about for the rest of the time. Prior attempts to fix the block diagram to account for non-idealities are incomplete. There's various ways of trying to fix up the model, but it hasn't been done completely up to now. Probably then we'll be ready for the break. And then in part 2, I'll talk about the General Feedback Theorem, which gives a block diagram as part of the result, not as an initial assumption. It turns out to be the same block diagram almost, but it's part of the answer and not part of the setup. And that's why you avoid having an incorrect model to begin with. And I'll do two examples. One of them is that same two-stage amplifier that I just used for the initial illustration. And the second example is a little more practical design example using a Darlington emitter follower, which has well-known potential for instability for certain ranges of the load capacitance. And the GFT, General Feedback Theorem, is a very useful method to do that analysis, and we'll see how you can actually come up with a design criterion to avoid an instability. In fact, to do better than that, because it's not just a matter of avoiding instability, it's a matter of controlling the amount of peaking of the output response and keeping that within an acceptable limit. So that'll be the final example. Okay, back to this infamous diagram. This is just a repeat of what we've had before with a definition of what is the loop gain. And the first thing you can tell about that, or I should say first, I've changed the G to an H because G is always associated with a gain, a voltage gain, or a current gain. But the GFT, General Feedback Theorem, applies to any transfer function of a linear system model. Any transfer function, therefore, including transimpedances, transadmittances, self-admittances. Any transfer function you want. In fact, we'll have an example of that too. So I changed the G to an H. So the H becomes a G, or it becomes a ZO for output impedance, or whatever the particular function is that you're interested in. Now right away you can see that that diagram is incorrect. Because it says, if A goes to 0, then H goes to 0. That's what the formula says. A being the forward gain of the amplifier. But you know, in any practical circuit, here's this same two-stage one again, that isn't true. Because if you yank the second transistor out of the socket, for example, then that makes the A go to 0. That's the forward path. But the input signal can still go from the signal source through the feedback path backwards and arrive at the output, giving you a non-zero output, even though the forward path gain is 0. So right from the get-go, that block diagram is wrong. Well, we can fix it. The thing we hadn't accounted for was the signal goes both ways through the feedback path, whereas when you draw that block diagram, we always draw the boxes as arrows, not as rectangles, because there's an implied condition. The signal is only supposed to go one way through each box. But since the feedback network is a passive network, almost invariably, it's bidirectional. And so that arrowhead does not adequately represent the reverse transmission through the feedback path. So let's put it in as a separate box. That's the H0 up at the top. So now we've accounted for that non-ideality. And it doesn't take much algebra to go through the solution for that, and you find that there's an added term, H0 times 1 over 1 plus t. And I've rewritten the first term again using this new definition of the H infinity, meaning that's the ideal closed loop gain if t were infinite, because then the second term would be 0. And you see that you have a weighted sum of two terms to contribute the total answer. H infinity is H when t is infinite. H0 is H when t is 0. That's when you don't have any feedback left. Now, every practical circuit has both extremes, because even if you start with a high value of loop gain at low frequencies, ultimately the loop gain is going to go away, and so the relative importance of each of those two terms changes places as frequency increases. The first term is important at low frequencies, and that's the one you're interested in. But ultimately at high frequencies, the first term goes away and the second one is left exposed. And you see that comes from the H0 box. That's the transmission through the feedback network in the wrong direction. Now, I've defined another couple of quantities here, which are not necessary, but it's useful to be familiar with the physical interpretation. The two weighting factors, t over 1 plus t, is called d, d standing for discrepancy factor, because it's the discrepancy between the ideal H infinity and the actual H that you're going to get. D0 is simply the complement of that. It's 1 minus D. It's the weighting factor for the H0 term. So a little more condensed way of writing that is the total closed loop gain H is H infinity D plus H0 times D0. Now, if you're designing a feedback system, this is backwards from analysis, as I already mentioned. You have to construct hardware that meets specs within certain tolerances. If you're designing a feedback system, you essentially go through 4 steps. The first one is to design the feedback network itself so that you get the desired ideal closed-loop gain H infinity. And H infinity is 1 over K. It's the reciprocal of the feedback path transmission. And everyone knows that. It's very easy to design that box. You just make a resistive divider whose value is the reciprocal of the closed-loop gain you want to get. So I've chosen an H infinity which is independent of frequency, but it doesn't have to be. It can be any frequency function that's required in the specification. Second step is you want to design the loop gain to be high enough so that the discrepancy factor, T over 1 plus T, is close enough to 1 so that the actual H you get is close enough to the H infinity within the allowed tolerances. That's easy in these days of integrated circuit op amps and so on. You got all the gain you could want. So it's very easy to meet that requirement. And in this picture, which is actually an example that I'll be going into detail later on, notice that the D peaks up a little bit. Not much, but a little bit in the neighborhood of the loop gain crossover. And as you probably know, if that peaking up becomes excessive, that's indicative of a too low a phase margin, and in the end, the peak goes to infinity and it's unstable. So that's step 2. And also, the next step that you're going to do graphically is to combine the D with the H infinity, which on the usual dB axis is simply a direct summation, and the H infinity times D, which is the closed loop gain H you're trying to get, is simply the sum of those two. And in this case, the H infinity is 20 dB, and H infinity D matches that up to a certain frequency, but then falls off below after loop gain crossover. This is the D0 term. This is the weighting factor for the H0 component. And you see that starts off relatively small when T is large, and it ends up at being 1 or 0 dB when T goes away. Then you multiply H0 by D0. H0 in this particular example is very close to 0 dB. It isn't exactly, but it's very close. And the final step is combining those two factors which are weighted. So the H infinity D falls off at high frequencies. The H0 D0 eventually takes over. And the total gain that you're going to get is the sum of the two, which on the log dB scale is simply whichever one is higher wins. So the actual closed loop gain is equal to H infinity dB at low frequencies, but after those two terms cross over, the H follows the bigger one, which is the H0 D0 term. And that's when you run out of feedback. Well, that shows the non-ideality of direct forward transmission through the feedback path, represented by H0 as an additive term to the previous result. Sometimes it's more convenient to express it as a multiplier term, and that's very easy to get to. In that top equation there, you see the sum of the two terms, and I just combine them together. And if I define that combination, H0 over H infinity T, as 1 over Tn, then you get the term at the bottom. Tn is the null loop gain, and we'll see why it has that name a little later on. And correspondingly, you can define a Dn as well, which is a null discrepancy factor. So when you use the Tn instead of the H0, this is the expression that you get. H infinity is what it was before. The denominator is 1 plus 1 over T as it was before, but you have a new term in the numerator now, And it's in the form of a multiplier dn instead of the added term h0. You see the format now matches completely what the extra element theorem format was. So we're getting closer to that now. So here's a summary as far as we've gone. This is the augmented block diagram, including the h0 term. Defines the discrepancy factor and the null discrepancy factor. And this is the basic result without the non-ideality, showing that the loop gain drops off at high frequencies and the closed loop gain follows it. And here's the added term representation. H is the sum of the two red lines. And here's the multiplier term representation. H infinity d is multiplied by dn, which is a direct addition on the log scale. And that causes the closed loop gain to level off as well. And if I go back to the previous one, you see that the H is identical in both cases. It's just that one is modified by an additive term and the other is modified by a multiplier term. Now a little terminology. The closed loop gain H is what I call a first level transfer function, or TF. And so far we found out it can be dissected in terms of 3 out of 4 second level transfer functions. Second level ones being H infinity, H0, T, and Tm. And there's a redundancy relationship between those 4 shown at the bottom. That was the definition of Tn in order to get it into the picture. But it is essentially a redundancy relationship because you only need 3 out of the 4. And these are the two ways of expressing it in the middle, one with H0 and the other with the Tn. Sometimes one's more useful, sometimes the other, and sometimes useful to look at both of them. They're alternatives. Now ultimately we want to calculate the second level TFs directly from the circuit model. We will do it first from the block diagram because there's some extensions needed which we'll do in order to get it directly from the circuit model. How do we want to find these second level transfer functions? One of which is the loop gain, and we already know that's a very important one. We want to do it by signal injection without disturbing the circuit configuration because we don't want to disturb the circuit determinant. That messes everything up. That's why we don't actually want to break the loop. We want to do everything by signal injection. And it doesn't disturb the configuration. Normally we inject a single signal, either a voltage or a current, and calculate a transfer function whose input is that signal. That's called a single injection or SI calculation. You got one input signal and you calculate any number of dependent signals in terms of that one input signal. A powerful analysis technique is to inject 2 signals, mutually adjust them to null some dependent signal, and calculate a transfer function whose input is one or the other of those 2 injected signals. That's called null double injection, NDI. And if you've heard anything about the extra element theorem, you remember that null double injection is the basic technique used to calculate one of those 2 driving point impedances, the Zn. Now, why is that relevant to this case? Consider this second level transfer function H infinity, the ideal closed loop gain. How can we actually calculate that from the circuit? The actual closed loop gain H falls short because the error signal, which is the difference between the input signal and the fed back signal, is not 0 if you don't have infinite loop gain. Here's the block diagram again. And here's an overlay showing the signal distribution under normal operating conditions where there's an input signal UI and an output signal UO, and there's no test signals anywhere. This is normal operation. The width of the overlay is a qualitative indicator of the strength of the signal in that particular branch. So you see the error signal is small. It's a thin line. It gets amplified in the forward path. You add in the direct feed forward through the feedback path, through the H0 box. The output is the sum of those two. The output is also fed back, which means attenuated, through the feedback path and subtracted from the original input, leaving the small error signal. And under those conditions, this is the normal closed loop gain H. Now, how could we modify the signal distribution in order to calculate H infinity instead of just H? What we can do is inject a test signal to sum with the error signal. In other words, to add to the error signal so that it drives the output a little higher. So now I've added a UZ. UZ is a test signal. And notice the error signal has gone down from what it was in the previous picture. And the output signal has gone up. UO is now bigger than it was before. Therefore, the fed-back signal has gone up. So when you subtract it from the UI, that's what makes the error signal go down. So that's self-consistent. I'll go back to the previous one again. There's no injected test signal. There's the test signal increased, and the output has gone up a little, and the error signal has gone down a little. Now, all you have to do is increase the test signal a bit more to make the error signal go away altogether. And the output signal has gone up again. But it's reached the value now of H infinity times UI. Because by definition, H infinity is the gain that you get if you had infinite loop gain. And by using the test signal, we have simulated infinite loop gain. Because the forward path produces a finite output from a zero error signal. Of course, it isn't really an infinite gain. We fudged it by applying the test signal in its place. But as far as the loop is concerned, we've simulated infinite forward path gain and therefore infinite loop gain. So the gain we're going to get is H infinity. Now, how do we calculate H infinity? Easy. Because the output, the fed-back output signal exactly balances the input signal, UI. So H infinity is UI over UO. UO over UI, I should say. And that's a very easy calculation to do. So that's one of the 4 second-level transfer functions. Most important one of all, in fact. How do we calculate T, the loop gain? Same model. Except this time we take away the original input signal, make UI 0. We inject a test signal, and it splits into 2 pieces. UX goes forward, gets amplified, gets attenuated in the feedback path, subtracted from 0, which reverses its phase, and comes back to the injection point as a UI. And so by definition, the loop gain T is equal to UI over UX. And this is the kind of technique that we've been familiar with for a long time. But that's not all we can do with this. We're back to the original condition, no test signal. Now, if instead of injecting a test signal to add to the error signal, if we extract an error signal to make the error signal bigger, the effect is to reduce the drive signal going into the forward path. It's because the test signal has diverted some of the error signal away from the forward path. So now the output has gone below H times UI. You can increase the test signal in that direction some more, enough to make the drive to the forward path actually go to 0. And what have we simulated now? We've simulated 0 loop gain instead of infinite loop gain, because there's no output coming out of the forward path. Therefore, if there is a non-zero output from the whole system, it must have come down the H0 box through the feedback path in the wrong direction. So this is how we calculate the H0. We inject a test signal, adjust it in the presence of the UI. That's null double injection until the output is 0. And you just calculate what the transmission through the H0 box is. And that's the value of H0. And it's a very easy calculation to do. So that's 3 out of the 4. We don't need to do the fourth one separately, but let's do it anyway. Then we can check redundancy. Keep on increasing the extracted error signal a bit more beyond this point. Now the drive to the forward path reverses direction, causing the output to fall still further. Increase it some more until the output actually goes to 0. What have we simulated now? We've simulated the Tn, because Tn is Uy over Ux, and the Tn is the upper loop instead of the lower loop. What's really happened is the signal through the forward path has been adjusted just to cancel the direct feed forward signal through H0, which is what makes the output null. That's why Tn is called the null loop gain. So we calculated all 4 of them. And this is just a proof that it's the same definition that I had in terms of the other 3. And here's a summary of those results. There's the 2 forms of the expression at the top, one with the additive H0 term, the other with the multiplier term, the redundancy relation, and the definitions of the second level parameters. H infinity is output over input with Uy nulled. That's a null double injection calculation. T is Uy over, I see a typo in there, Uy over Ux, it should be, not Ui in the denominator. That's a single injection calculation. Direct forward transmission, H0 is U over Ui with Ux nulled, null double injection again, and the null loop gain is Uy over Ux with the output null. So that's a summary of where we are to this point. Next question is, are the Ux, Uy, and Uz voltages or currents? The answer is, it could be either. In fact, we already know that because those are the typical examples that we've been dealing with for a long time. Except in the past, you had to choose one or the other, and neither one was accurate unless that impedance ratio looking backwards and forwards was sufficiently small. Here's an example now how we can calculate these second level transfer functions in a little more practical circuit. This is a basic inverting op-amp configuration. It's the integrated configuration if the R2 were a capacitor instead of a resistance. Very simple model, and I'm assuming that the forward amplifier has a transconductance at 0 frequency of 110 milliamps per volt, and it has 2 poles, one at 10 kilohertz and one at 700 kilohertz. There's a resistance Ri there that isn't really essential in the basic model, but you'll see the reason that I've put it in a while. At the outset, you can tell that the Ri doesn't influence the result very much because it's connected across the front end of the op-amp, and that's almost a virtual ground to the extent that the loop gain is very large. So there's very little signal in Ri, and it makes hardly any difference to the final answer. Now, the object of building this circuit and choosing the values of R2 and R1 the way they are is because we expect the H infinity to be R2 over R1. That's why we designed this, because we know that the H infinity is the reciprocal feedback ratio, the 1 over K, and that is the feedback ratio. So how can we calculate make sure that the H infinity for this circuit is indeed R2 over R1? Well, from the block diagram with the overlays I just did, you see that the way we can do it is to add a test signal so that it adds It subtracts, I should say, from the error signal going into the forward path. Point P1 is a point suitable for ideal voltage injection. It's ideal because it's looking into an essentially infinite input impedance of the forward path. So let's put a signal in there. There's an EZ. This sets up a voltage Vx going forward that comes back around the loop as a minus Vy. Now, how do we adjust EZ in order to calculate the H infinity? Well, in the presence of the EI, we adjust EZ so that Vy is null. Well, here's the condition. I've written them in red. You adjust EZ relative to EI so that Vy is 0. And that means there's no current in Ri, because it's got 0 voltage across it. It's been nulled. Therefore, the current down R1 is equal to EI divided by R1, because the point P1 is a virtual ground now that you've nulled Vy. And no current goes into Ri, so all of the current in R1 goes down the R2. The voltage drop across R2 is R2 times EI over R1. But therefore the output voltage, VO, is R2 over R1 exactly. No assumption of infinite gain anymore. We have simulated infinite loop gain. And the answer is exactly R2 over R1. And the notation I've used there with that superscript Vy, that's to indicate that Vy is nulled in order to solve for that quantity. And you see how easy a calculation that is. And this is typical of all null double injection calculations, which I spent a lot of time emphasizing in the extra element theorem seminars. It's easy because you never have to know what the adjustment is between the two sources, EI and EZ. You never have to know what it is. All you have to know is that the null is set up. And you use the null to calculate the answer you want. And the answer you want in this case is what is VO in terms of EI. And using the 0 or null Vy is all you need to use to do that. In other words, using the fact that the null exists is equivalent information to knowing what the adjustment of the two sources is. But you see, if you were to try to do that calculation by conventional methods, you'd have to use superposition. You'd have to find the output that results from EI. You'd have to find the output that results from EZ, add the two together, and then find the condition between the two sources that makes the Vy null. But you don't have to do any of that. You simply use the fact that the null exists to get the answer you want. And it couldn't be easier. You do it by inspection. Here's the T. This is a single injection calculation anyway, because the EZ is the only signal injected. The EI is 0. And without going through the details, you start with Vx, you multiply it by the op-amp gain, which is the GM at 0 frequency, to find the 0 frequency value of loop gain. Then you go through a couple of dividers, and that's the combination of resistances that you see there. Now that's a low entropy form. Don't multiply out those series parallel combinations, because all you get is a ratio of sums of products of the circuit elements, and you've lost all the useful information to work backwards for design. So derive the answer in that form and leave it in that form. That's where the useful information resides. So that's the low frequency value, and all you do is multiply that by the two poles to get the frequency response. Here's the third second level transfer function. This is the direct transmission through the feedback path. Again, double injection. And you adjust EZ in the presence of EI, this time to null Vx. If you null Vx, there is no signal going down the forward path. So that output current source is 0. So all you're left with to find VO is a pair of dividers. The RL is a divider back to point P1. P1 is a divider back to EI. So it's simply the product of two divider ratios. And the answer is a little under unity for these particular numbers. Here's the fourth one. The null loop gain. Double injection again, but adjust EZ this time to null the output voltage VO. Start with Vx and follow it around the loop to Vy. Again, this is so easy you do it by inspection. Vx is multiplied by the GM. That provides the output current from the forward path. Now, there is no current down RL in this case, because RL has 0 voltage across it. We've nulled it on purpose. So all of that output current has to go down the feedback path. And Vy is the voltage at the left-hand end of the R2. So Vy is the voltage across R2, but since the voltage at the right-hand end is already null, Vy is simply the drop in R2, which is Gm times R2. And that's the null loop gain. That's all there is. Now we calculated all 4 of them. We only needed 3, but you can check the redundancy, which is in fact correct. If you put the numbers in from the last three slides, you find that those 2 ratios, each one of them is equal to 12. Notice that the Tn was a simpler result from a shorter calculation than the H0. And that's usually the case. And that's one of the benefits of using the Tn format instead of the H0 format. It's an easier, shorter calculation. So again, there's the 2 versions in the middle. First and second versions. This is a repeat because I keep trying to re-emphasize these because it's a little different format from what you may be used to. Now, that was the analysis with some numerical values to check out the redundancy. Now, how can we actually do this with a circuit simulator? Intersoft has incorporated this injection and nulling technique into their ICAP4 software. And all you have to do to utilize that is take your original circuit that you would analyze in the first place and choose one of the templates that's provided in the software. And this is the template that injects a single voltage EZ. And all you do is connect that box to the place that you want in the circuit. So the Vx is connected to the forward amplifier. The Vy is connected back to the feedback tapping point. Now, because the template is going to do null double injection calculations, it also has to provide the input signal. So you take away the independent signal that you had before and simply connect it to the right terminal in the box. And some of the calculations are going to involve nulling the output, so you have to null the output. So you have to sense the output and connect that to the appropriate terminal in the template. And that's all you have to do. Then you run the software, and it gives you all 4 of the second level transfer functions. It also calculates the original circuit gain without any test signal injection at all, just so you can check that the theorem gives you the right answer. You can display all the transfer functions as magnitude and phase Bode plots. And in fact, those are the plots that I used already when I was describing the steps that you go through. And here's a few more of the individual results. First thing to do is check that the H infinity is what was expected. And there's a typo in that title again. That should be H infinity in the top line. You've chosen the injection point and the injection signal in order to get the value of H infinity that you want, namely the resistor ratio of the feedback path. The H infinity shown in this graph is the output from the simulator, and it is indeed flat at 20 dB, confirming that you've done the injection properly. All right, I should say you've chosen the right injection setup in order to get that answer. It also shows TV, because this is a voltage injection calculation, so it's got an extra subscript V on it. TV is high at low frequencies, and it crosses over, and the TNV is larger than the TV in this case, and crosses over at a somewhat higher frequency. This is to check that the calculated value of H is the same as H by direct calculation. And notice I've shown the two discrepancy factors also, the D, which is T over 1 plus T, and the Dn, which is 1 plus 1 over Tn. You multiply both of those with the H infinity, and you get the result for H, which is the correct value for that circuit. Let me back up a minute on that one. Notice that the H does what you expect. It's equal to H infinity at low frequencies. It peaks up a little bit before falling off, meaning that the phase angle is not great. But it doesn't go to zero at infinite frequency. It levels off at just about 0 dB. If I drew this at a bigger scale, it would be just under 0 dB. Why is that? It's because the H0 term has taken over. It's the direct transmission to the output through the feedback path that is determining the output at high frequencies, even though the op-amp gain has gone to 0. So that's an important difference, which you would lose if you don't account for the direct forward transmission through the feedback path. Big difference. Now, notice that the format of this augmented theorem has a 1 plus 1 over Tn in the numerator and a 1 plus 1 over T in the denominator. Now, you can manipulate that and put it all into the form of a 1 plus 1 over Tp. You can force it into that form just algebraically, and here's how you can do it. I don't have to go through the step. The answer is H infinity times 1 over 1 plus 1 over Tp, where Tp is a pseudo loop gain, because it contains both the T and the Tn. In other words, you've forcibly tried to hide the non-ideality term by modifying the definition of the loop gain. Now, sometimes that's a useful thing to do, but not always. And this is an example where I don't think it is very useful to do that, because here's the Tp. That's the red line. And it's hard to correlate the shape of Tp by looking at the circuit. The Tp is large at low frequencies and it levels off at high frequencies, and it's hard to explain exactly why the circuit does that. And the reason is because it's actually a combination of both the T and the Tn. Here's a different injection point for the same circuit. This is showing single current injection now, which you can do at the output of the forward path because that's a dependent current generator. It's an ideal current injection point. There are the results that we got for the voltage injection that we just did. I made them all blue this time as a reference. And superimposed on it is exactly the same result for the current injection that I just had in the previous picture. And they're identical. because the first one was an ideal voltage injection point, the second one's an ideal current injection point. They both give the right answer. Now, from here on, we're going to see why things can go wrong from here on. Same circuit again. Voltage injection has been shifted now. It's on the left side of the RI instead of the right side. A pretty small difference, you think. In fact, I'd already mentioned that the presence of the RI anyway doesn't make much difference. But we'll see right now that when the test signal injection is on the left side of the RI, this makes a big difference to the answers that you get. Now, if you compare that with the previous pictures, you see the red line now is the voltage gain with the RI on the other side. And the phase angle and the magnitude are both completely different at higher frequencies from what they were at the ideal voltage injection point. Now this is another warning that you have to be very careful where you do the injection if you're going to get the answer that you want to get. Because you see, you can get huge differences. Now, why is it different? This is the reason you get a difference in the loop gain TV. Consider infinite frequency, just to take an easy case. The op-amp gain has gone to 0 because of the two poles, so I just took it out of the picture. Now we're going to calculate Vy over Vx at infinite frequency for this particular condition. And you see Vy over Vx, the loop gain, is not 0, as it should be at infinite frequency when the op-amp gain goes to 0. In fact, you can see what the Vy over Vx is. You've got the same current going through Ri as you do on the other side. So Vy is approximately equal to R1 times Iy, and Vx is equal to Iy times Ri. So TV is R1 over Ri and is not 0, the way it should be. So the conclusion from this is, if you have a non-ideal injection point, meaning that the impedance ratio looking forward and backwards is not sufficiently small, and it's not in this case, the loop gain does not go to 0 when t goes to 0. It goes to the impedance ratio itself, because that's all this is. It's the ratio Ri on one side to the R1 on the other side. Vy over Vx will always end up at that ratio, even though the proper value of the loop gain should be 0. So the conclusion is a non-ideal injection point gives a Uy over Ux that depends not only on the true loop gain, but also on the impedance ratio, looking back and forth from the injection point. And that's what you have to be careful about if you're going to use this technique. That's not the only difference. That's what happens to the loop gain. You get the wrong answer for loop gain. But you also get an H infinity that isn't what you want either. If you look at the top pictures on there, the red H infinity is a whole lot different from the blue and the green H infinities. The red one is from the non-ideal injection point we just did. The blue one is from the ideal voltage injection, and the green one is the ideal current injection. And the blue and the green are the same, and they're the answers you expect to get, flat, at all frequencies for H infinity. The red one is nowhere near flat. So the conclusion is you get a very different answer if you don't use an ideal injection point. The reason for the difference in the H with Vy node, you want it to be H infinity, but it isn't, and the answer is, again, the Iy is not null, even if the Vy is null. And we're getting now to the important thing that we have to fix in order to get the right answer. Because we see that even if you null the Vy, which is the error voltage, this does not mean that you get a nulled Iy, which is the error current. That is, when you have the Ri on the wrong side of the injection point. So looking back from where we are at this point, single test signal injection, voltage or current, delivers a block diagram that includes H0. That's the thing that's been added, which represents direct forward transmission through the feedback path non-ideality. The limitation of that is it requires an ideal injection point. According to that definition of the impedance ratio, it has to be small for either case. This is where we're going next. We're going to find out the dual signal injection of both voltage and current delivers an exact block diagram that includes all the non-idealities. And this is where I predicted in the outline that we would take a break.